And I'm supposed to start the party preparation, but an unfortunate thing happened to the team of the reporter, the team of China. They didn't realize the part of regulations which says that in final, and specifically only in the final, each team member can appear at the stage only once. So they've used their reporter already for opponent, or I don't know, reviewer. And now they have to find another team member to deliver the report. So it's a very unfortunate situation, as you all might understand. And I think we should give them a few more extra minutes to adjust. Although, like, it's really their problem and their issue because it's written clearly in the regulations. We have checked it in the book. Still, I think it's like within the spirit of fair play that the new reporter gets a chance to get a few minutes for absorbing all the knowledge needed for the report. Yeah? No, but there is no regulations about how long the break between the fights is supposed to be. Sorry, but between the stages. So like we had 5 minutes, we had 10 minutes, we had 15 minutes. So it's not like half an hour. But I think if we have like 2 or 3 more minutes for them, I suppose it's fair because it's just like yeah, in the spirit of fair play, because that's a big obstacle for that tournament.
Not good. No, it's not. Oh wow, Martin, you have to look at these people all have some sort of back. All have like Olympiad backwards.
好像有2个30 iPhone。
对啊，that's okay. They should all have Olympiad backwards. Not like iPhone, but they are going down that path. Not in China for their like people have external glasses.
Can you specialize?
No, like they tell you to do it external. They give you external stuff, you have to learn how to do it. This might be the miracle. Maybe. I don't think it's that hard of a question. It's not that hard of a question, but maybe the minute details. Like, how did you measure this? I don't know. Pass me some notes.
All the notes.
And Singapore is getting close by Germany. Which is like, okay. So much confidence in their kids, or they know that they already
Okay. We start the clock now, and we start the preparation time 5 minutes for the team now.
Everyone speaks in different language.
太师级的那个好像他在干嘛？
No, I think they're just trying to calm their nerves. Like, they don't care. Maybe this was their plan all along. Maybe it's their plan. Why do they look so pop? They're like not even talking to each other. Underestimate whole sense of hope. Really, they're gonna pull a 10 in the report, and they're just like all laughing on the inside. Like, oh, this is a third year. We're very deceptive, eh? Is there, no, that's not like all looks real happy. Martin's going off for Germany. Martin wins. This is better than going to a movie theater. This is like live entertainment. So much excitement. I finally understand why people like watching sports so much. Just see the greatest upset.
家长跟家长
They have to make sure you leave this way. Safely. And honor yourself. This is like
Okay, we have like 5 more seconds for the preparation time. And yeah, just before we start, I would like to remind every one of you that within the regulations we have a regulation that says that like specific comments, answering specific questions, and short interrupt and join of the discussion is also allowed to the other team members. So in this like very special case where the reporter is not land reporter, we might see this happening. So it's fully according to the regulations as long as it's not too excessive. So certainly the other person in the team is not supposed to take over the discussion, but clearing specific points from a theory or experiment, and also for like then the jury members answering the specific question from the jury. It's fine if it's done by another member of the team. So That's something I expect could happen now. But I think you are ready as far as you can be ready under the given circumstances, so please start.
Yeah. Good morning, ladies and gentlemen. I'm Yang Haichuan from China, and today I'll be presenting problem number 3, dancing coin. Let's first have a quick review of the problem. We are to take a strongly cooled bottle and place a nickel coin on its neck. As we can see in the video, the coin would dance in a rotatory motion. So our observations include that the coin dances in a flipping motion. In addition, some noise is triggered upon the collision between the coin and the bottle. We then identify the relevant parameters as the initial temperature of the bottle, the radius and thickness of the coin, and the bottle type. Here are our contents for today. Firstly, I'll focus on the heat transfer process in the phenomenon, including the closed bottle and the escaping gas. Then, I'll focus on the dancing coin's dynamics. Further moving on, we'll look at the noise and its causes. Finally, we'll move on to further insights. So, firstly, to model heat transfer, we need to consider the closed bottle between the nth jump. In this state, the gas inside the bottle has a certain pressure and temperature. Treating the air inside as ideal gas, we can write the equation as such and use the process equation with the Newton's cooling law, where K denotes the cooling coefficient of the bottle. This is a parameter that's relevant with other parameters as shall be covered later. Then, we consider the escaping of the gas during the nth jump. In this process, the part of the gas we consider will change in its number of molecules and the volume. We can similarly write the ideal gas equation as such, where the process equation can be treated as adiabatic. In this equation, gamma denotes the adiabatic coefficient. So, in order for both equations to work, we need to note that the process is quasi-static. By analyzing relevant parameters, we find that the speed, running a simulation, we find that the speed of the air inside the bottle is significantly smaller than that of sound. Therefore, both equations apply to this scenario. So now we can obtain the dancing interval between two jumps. Now, the PC denotes the critical pressure for a coin to jump up, and K denotes the cooling coefficient, which is relevant with both the geometry and surface of the bottle and humidity and airflow in the environment. To determine this coefficient, we measure them from experiment. We track the evolution of the temperature of the bottle over time, and then calculated the temperature discrepancy between the bottle and the room temperature. We then fit the curve using Newton's cooling law and obtain the cooling coefficient as such. Now, in the following section, we'll focus on the determination of the critical pressure, which is relevant with both the geometry and location of the coin and the surface tension at the bottle neck. So, we'll now focus on the dynamics of the dancing coin. When the coin rests at the neck of the bottle, we must understand that if the coin was to dance, it has to rotate around a certain pivot. Therefore, we can write a gravitational torque as such, which is the persisting torque. In addition, due to an increased pressure inside the bottle, this pressure serves as a driving force, and then we can derive the critical pressure for gravity of the coin. However, we note that in reality, a coin sometimes deviates a certain distance from the symmetry line. Then we can write the new equation representing the critical pressure for a coin to jump up. We can see that this deviation of the coin will result in a smaller critical pressure. Thereafter, we conclude that the asymmetry of the phenomenon requires less energy for the coin to jump up. Then we'll look at the surface tension at the neck of the bottle, namely the water membrane inside the bottle neck and at the outer edge of the nickel coin. So, the surface tension due to water film can be written as a combination of these two origins. Then, we measure them using a Joule scale balance And then we can see a good agreement between the theoretical prediction of the surface tension and experimental measurements. So now we have both considered the coin's gravity effect and also the surface tension around the bottleneck. Therefore, we derive the critical pressure for a coin to jump out from the bottle. Then we measure relevant parameters of our coin and bottle to find that surface tension indeed cannot be neglected. Therefore, we find that the critical pressure for the coin to jump up and the heat transfer rate is obtained. This allows us to further predict the time interval between two jumps. So, in order to verify our theory, we track the time interval between two jumps in relation with time. We then plotted our theoretical prediction using the equations mentioned previously, and we find that they agree mutually. We find that the dancing interval increases over time as the temperature difference gradually decreases. And as the temperature difference decreases, there's less heat flux flowing inside the bottle, and therefore more time for the air inside the bottle to reach the critical pressure. We then carried out experiments by changing the initial temperature. We find that as the temperature is increased, or in other words, the bottle is less strongly cooled, the dancing interval increases. The temperature in our experiment is controlled by a refrigerator, which we can monitor the temperature inside. This indicates that our qualitative explanation as to why the coin dances is correct. In addition, we also varied the mass of the coin. We fixed different numbers of coin together and put it on the bottle's neck. We find that it takes more time for a heavier coin to jump up from the bottleneck due to an increased critical pressure. So even when other parameters of the bottle, including its volume, surface states, are kept the same, which means that the cooling coefficient is the same, because the critical pressure increases, the dancing interval increases as well. Finally, we varied the type of the bottle to find that when we use a plastic bottle, the time interval increases at a certain time, and then the coin stops jumping. This difference is caused by the cooling coefficient of the plastic bottle being lower than that of the glass bottle. In this case, the heat flux flowing through a plastic bottle is smaller than that of a glass one. Now we are ready to look at the noise. So using a microphone, we are able to report the noise when the coin jumps. This is the FFT diagram we obtained from the recording. In order to explain these peaks on the FFT diagram, we explored different possible causes of the noise. Firstly, we blow air in around the bottleneck to find that the resulting frequency is very low. It is in a range between 0 and 2.5 kilohertz. And this frequency corresponds to the lowest frequencies in the complete sound profile. Therefore, we conclude that the lowest frequencies are caused by the resonance of the air inside the bottle. Thereafter, we hit the coin with the neck of the bottle to find that there are two peaks in the FFT diagram. Therefore, we conclude that the sound waves excited due to oscillation excited by the collision correspond to the two frequencies in the complete sound profile. And the reason there's two frequencies is because that the bottle will oscillate in both the axial and the radial direction. Therefore, until now, we have explained all frequencies of the noise. Now we are ready to look at some further insights. So, if we track the time, if we track the dancing interval to over 15 minutes, we find a large discrepancy between the theoretical prediction and the experimental measurements. To fix this, we observe the surface of the bottle. we find that at a certain time, the bottle will transition from first phase to the second phase. In the first phase, the vapor in the atmosphere will condensate due to the low surface temperature of the bottle. However, after a certain time, as the temperature of the bottle surface increases, some of the vapor liquefies as the temperature increases, and some of the originally condensed water will also melt. And it is this phase difference between condensation and liquefaction that causes a difference in the cooling coefficient of the bottle. So to fix this, we measure the cooling coefficient before and after the phase transition. And we can measure the corresponding cooling coefficient for both phases. Then, plotting the theoretical prediction in corresponding regions, we find a good agreement between theory and experiment. So, in conclusion, we have determined the driving force of the dance due to the heat transfer between the air and inner and outer sides of the bottle. We then change relevant parameters and find that as time progresses, the time interval increases as the temperature difference decreases. Other means to reduce the temperature differences will also increase the dancing interval, for example, by using a higher initial temperature or a plastic bottle. In addition, we find that a heavier coin will result in a slower dance due to increased vertical pressure. We also explain the causes of the noise, including the resonance of the air inside the bottle and oscillation of the bottle due to collision. And that's all for my report, and thank you for your time.
Thank you. Time for questions from the audience.
Thank you to the reporter. What is the maximum amplitude of the flip of the coin that you observed?
We observed a maximum of 2 millimeters in the flip.
In the Y direction, I see.
Yes.
So can you go to slide 5, please? 5.
Yes.
Okay, so in your thermodynamic theory, do you assume a steady state heat flux?
No, the heat flux is changing because the temperature discrepancy decreases over time.
I see, okay. So can you go to slide 7, please? Slide 7, yes. So I noticed that the phase velocity of the air you use is 340 meters per second. I believe this is the velocity of the speed of sound in room temperature air. So do you use room temperature? Do you account for the cooling of the bottle in the calculation of the speed of sound?
Yes, the speed of sound will vary with the room temperature. However, you can see in our simulation, we can just perform an analysis on the order of magnitude to arrive at this conclusion that the velocity of the air inside is significantly smaller than the speed of sound.
Okay, can you go to slide 12, please?
Page 12.
So did you model the slipping of the coin as it flips?
We did not model the slipping.
I see, thank you. Can you go to slide 18, please? So the heat transfer coefficients that you use were characterized experimentally, right?
This coefficient is measured by tracking the time discrepancy between bottles.
So was this characterized experimentally or was this fitted?
This is measured experimentally.
I see. Do you have any investigation into the dynamics of the coin?
Yes, as I stated in my report, our whole dancing trajectory is the dynamics of the coin.
The trajectory.
I'm sorry, the question seems to be quite elaborate, so I would suggest to leave it for the discussion. 3 minutes time for preparation of the opponent. Thank you.
Good afternoon, everyone. I'm Russell Young from Singapore, and today I'll be opposing problem number 3, dancing coin. So here is a summary of the report. The reporter has given a qualitative explanation as to why the coin lifts up due to a pressure build-up due to heat gain in the bottle, and he has modeled the heat transfer and motion of the coin with surface tension considerations, and in his experimental scope, he varied the initial temperature, radius, and thickness of the coin. So here are some strengths and weaknesses of the report. The reporter has a quantitative model of the coin flipping using Newton's law of cooling, and he has explained how this affects the flipping frequency. And I feel that this is an important part of the phenomenon since the thermodynamics directly governs the flipping interval and the flipping frequency. And his use of Newton's law of cooling is sufficient for the thermodynamics. And there is also an analytic expression for the time interval between flips against various parameters. And this is rather commendable since this allows us to see the effects of various parameters on the flipping interval. And there was an experimental verification of the flip intervals as well, but this will be discussed later. However, there are many areas of improvement of the report, and there is no experimental investigation into the dynamics of the motion of the coin. The problem statement clearly asks us and tells us that we will see movements of the coin and we will observe a dance. However, there was no experimental investigation into what happens when the coin lifts up and the trajectory of the coin as it lifts up. And I feel that he could have simply investigated this by putting a camera close to the bottleneck and tracking the trajectory of the coin as it lifts up over different flips. And this is an important part of the investigation that was completely neglected in his report. There was also no systematic investigation into the source of sound, as there was an unsatisfactory explanation for the lower frequency sound. The reporter has explained the source of the lower frequency sound to be that of the air resonating between inside the air, the air inside the bottle, the resonance of the air inside the bottle. However, he did not provide any quantitative model, and he could have modeled this firstly using by modeling it as a Helmholtz resonator, and number two, he could have varied it experiment. And we note that the Helmholtz resonator depends strongly on the volume of the bottle, and he could have varied the volume of the bottle simply by filling the bottle with different amounts of fluid and recording the frequency at which that is being heard as the coin flips. And there was also no systematic investigation into varying the coin radii. And since varying the coin radii will result in different frequencies, and there was also no quantitative investigation given into this. And I felt that he could have investigated this by modeling the coin as a thin plate and using thin plate theory to model the natural frequencies of the coin as it oscillates due to its collision between the coin and the bottle. There was also a limited theoretical model since he did not account for slipping of the coin. And we can see in his experimental video very clearly that as the coin lifts up, that the contact point will slip. However, this was not modeled, nor was this discussed, and this perhaps lead to, and he could have simply modeled this using Newton's second law. And this would result in this could explain the deviations in his experimental data. And there was also the effects of the speed of sound were not modeled. So, for example, in the acoustics of the phenomenon, the speed of sound will definitely change with the temperature of the bottle. However, there was no account given into this. And there is also the use of discrete cooling coefficients for the use in the heat model. And I feel that this severely jeopardizes the integrity of the heat model, since he cannot account for time dependency of the characterization of the coefficients, and he could have simply done so by placing the bottle on a weighing scale and measuring the rate of change of mass due to condensation with the latent heat of vaporization to model the heat flux, then using the heat equation. And there was also a poor experimental scope since he did not vary the surface tension coefficients. Since a higher surface tension coefficient will affect the flipping frequency, and he could have used a slope solution to do so. So now I would like to invite the reporter up for a discussion. And first, may I refer you to the slide on the acoustics of the phenomenon. So could you go to the slide?
So just to announce, we are starting the discussion.
Yes, we are starting the discussion. So could you go to the slide with the two peaks of the sound?
Yes. 1 second, please.
Yes, so I noticed that you have two peaks of the sound. So this is the spectral power frequency. This is the amplitude, and this is the frequency.
Right.
I noticed that you have a small peak here, and you have
Could I kindly ask you to move the
here.
whiteboard a little bit towards us, because we
Yes, so you have two peaks.
Yes.
So you attribute yeah. So can you please explain the source of this lower peak?
This is due to the hardmost sending wave inside the bottle. And so the opponent has mentioned about quantitative calculation of the frequency. I believe that by applying relevant equations into our simulation, we can indeed
What are
calculate.
these relevant equations that you inputted into your simulation?
Because I believe that the main aim of this problem is to investigate the source of the noise, and I think to calculate the exact frequency will not be necessary.
I think it is necessary because the frequency of the noise is an important part in allowing us to determine the source of the noise.
So what I like to point out is that when we record the noise of the dancing, we find that the frequency is it can be influenced by random parameters.
Yes.
And that will result in a major difference.
Yeah, and I think one relevant parameter that affects the frequency of the smaller peak is the volume of the bottle. So if you have a volume of the bottle that is smaller, surely you will hear a higher frequency.
That's right.
So you have conducted a systematic investigation by filling the bottle with water.
I think that filling part of the bottle with water will change the thermodynamic properties of the bottle, and therefore will also change other states in the process, including the heat transfer and the dancing of the coin. But I think that calculating the frequency can indeed be achieved by applying equation.
Yeah, so the relevant equations that I believe the reporter is saying that can be applied is the equations known as the Helmholtz equation to model the bottle as a Helmholtz resonator.
That's right.
Yes, and I think this could have been done to explain the position of the smaller peak.
I agree, and I'd like to also add that we have already analyzed the source of the noise as that frequency. Yeah,
and the larger peak can definitely be explained by the natural vibration of the coin.
The two peaks can be explained.
The second peak, the
largest peak can be explained by the oscillation of the coin.
Yeah, and this can definitely be modeled perhaps using a thin peak theory. Do you think this is possible?
So what equations are you actually referring to?
It is the equation that governs the flexural rigidity of the coin and the bending of the coin undergoing free vibration.
Yeah, so how do you plan to model the surface tension around the coin? I think that the surface tension and the water membrane will also cause some deviation to the oscillation frequency.
Yes, I understand that the surface tension might result in damping effects that could affect the position of the frequency of the coin. However, I think that first step at a model would definitely be to model the vibration of the coin.
So if we consider a dry coin and compare that to a coin with around a water membrane on its edge, so do you think that the frequency will increase because of the water membrane or decrease it?
The frequency will definitely, well, it's very hard to say, but definitely the frequency will change due to damping effects.
So what's the amount you think it will change?
I think this is insignificant. Less than 5% because the mass of the water is much smaller than the mass of the coin.
Okay, I agree. So actually by calculating the frequency, you may see a fit between the theory and measurement, but still we have qualitative attribution of the highest oscillating energy to the oscillation of the coin.
Okay, so I see that we have enhanced mutual understanding, and I think this is definitely one of the most important parts of the phenomenon. So let me allow you to move on to the slipping of the coin. Could you perhaps go to your graph of the flipping interval, where it underpredicts the flipping interval? I believe this is slide 15. We perhaps go to slide 15, please, and we show the theoretical fit. So I see that your theory constantly underpredicts your experimental points at very large times. So I think one possible reason is because as the coin flips, that the contact point will slip. So I think one reason the contact point will slip, do you think this could be modeled?
I disagree, because if you can see in our experimental video, we observed no slipping of the coin horizontally. And if I can borrow this one. So before each experiment, we sanded the neck of the bottle using sandpaper between placing the coin above. So the surface of the neck is relatively has a relatively high coefficient of friction, and therefore we observe no slipping. So I think the reason why you mentioned slipping is that as a coin flips,
yeah, this contact point will most definitely move, right? If it slips.
Can we see the experimental video? And I think that we observed no horizontal slipping. So, and I think that one reason of the slipping is because the pressure inside, when it reaches critical pressure, is higher than atmospheric pressure and will cause a driving force, a normal force on the coin. And because of the inclination of the coin, there might be some horizontal component.
Yeah.
However,
so
in our experiment,
when the normal force is not sufficient to maintain the slipping, to maintain the coefficient of the frictional force, right?
However, in our experiment, as I said before, the maximum height of the dance observed is 2 millimeters. And if we compare that with the diameter of the coin, the diameter of the bottleneck, which is approximately 2 millimeters, 2 centimeters, we see that the inclination is rather small. And in fact, through calculation, we find that this inclination is smaller than 5 degrees. So therefore, I think that the horizontal force is insufficient to cause horizontal slipping.
So I thank you for your explanation. And I think that slipping effects are important when we increase the initial temperature difference between the bottle and the atmosphere, and this will result in a higher amplitude of flipping of the coin that can result in a lower normal force, and it can perhaps result in the coin flipping. So this could perhaps result in your theory being more generalizable to a larger range.
I disagree that increasing the initial temperature discrepancy will result in a higher flip. This is because in our theory, the reason why the coin dances is because the pressure inside will overcome both the coin's gravity and the surface tension. And increasing the temperature discrepancy at the initial state will not change such criteria.
So I
Which
see
means that as soon as the pressure inside reaches the critical pressure, the coin will jump. And actually, by measuring, you can see that the height of the flip is uniform across time.
So firstly, I would like to commend the reporter for accounting for these slipping effects by sending down the surface of the coin. And since we are discussing on the dynamics of the coin, we'll perhaps give an account and draw the trajectory of the coin. So let this angle be theta of the coin. We'll perhaps draw theta as a function of time. So the trajectory of the coin as it flips up and lands back down.
I think that firstly, because at the start of the jumping, because the water membrane breaks, so there's a net vertical force on the coin, which is actually equals to the magnitude of the surface tension, and it is due to that this discrepancy that the coin will have an initial angular acceleration.
Okay, isn't the initial gradient wrong? Because the coin is flat at the start, then it will start to slowly increase in the
the coin will gain a certain amount of angular acceleration at the instant of the start of the dancing. As you can see that, so right before the dancing, we can see that there should be a equilibrium between the external and internal pressure. So when the coin starts to jump, the water membrane breaks.
This doesn't govern the trajectory of the coin, because seeing as the trajectory you've drawn here, I would expect that this is when the film breaks, right? And this is when
the film breaks immediately.
Why does the film break immediately? I see that as the coin lifts up, the film will definitely take some time to break, right?
I think that time can be ignored, and so I'd like to carry on to my explanation. So as the coin jumps up, the water membrane breaks, and we can see that the internal pressure now becomes greater than the external pressure, and this causes an instant angular acceleration of the coin.
Yes. So I would like to. So this will result in this instant acceleration of the coin that you see here, and then subsequently the coin will go into free fall.
Yes.
And you could have investigated this by placing a camera next to the coin, since this is one part of the problem statement they are tasked us to investigate.
Thank you. Thank you very much. The time for discussion is over. Thank you. And your opponent has 1 minute.
Okay, so during the discussion, we talked about the sources of the acoustics of the phenomenon, and the acoustics is definitely one of the most interesting parts of the phenomenon. And the reporter has given an unsatisfactory qualitative explanation into the sources of the sound, and I gave a suggestion as to how he could have conducted a systematic investigation into the sources of the lower frequency sound and the higher frequency sound by varying the volume of the bottle and the radius of the coin respectively, and modeling them as a Helmholtz resonator and using thin plate theory. And we also had a discussion onto the qualitative effects of the slipping of the coin, and I would like to commend the reporter for accounting for this in his experimental control by sanding the surface of the bottle down to prevent slipping from occurring, therefore increasing his experimental control. And there was also no investigation. We also discussed why dynamics was not modeled, and I feel that this is definitely an interesting part of the problem, since it is part of the dance of the coin, and it's very unfortunate that this was not done. So in conclusion, I felt that the reporter has missed out on the most interesting parts of the phenomenon.
Thank you very much. And Time for questions from the reviewer, please.
First of all, to the reporter, thank you very much first of all. You used ideal gas law to describe the pressure inside the bottle, correct?
Yes.
Can you name the main assumptions that need to be given in order to use the ideal gas law?
Sorry?
Can you name the main assumptions that need to be given in order to use the ideal gas law? Opponent, do you want to give a hand?
The main assumptions that allow you to use the ideal gas law are a low pressure. Since at high pressure, we need to consider intermolecular forces between molecules.
This is correct, and we also analysis the order of magnitude by considering relevant parameters in the original van der Waals equation.
And did you prove the assumptions for the ideal gas law?
We have a just wait a second.
Okay, no. Could you go on slide number 15, please? Sorry. And did you measure the pressure in the bottle, and where and how did you measure the temperature in the bottle?
We did measure the pressure, and because of technical issues, I'll draw on the board. So we measure the pressure by putting a pressure sensor inside the bottle, which has a minimum effect on the thermodynamics. And also, so measuring the temperature.
Did you measure the temperature at one point on the bottle?
We measure the temperature by fixing
So at one point.
various metal plates
Okay.
inside the bottle, and
So
then
it was an average.
use a infrared.
Okay, thank you very
thermometer.
much. Could you go on slide number 15, though, please? Or is it still not working? Okay, I'll just go on with the next question. You simulated the heat distribution inside the bottle. Did you simulate it,
Yes.
or did you actually measure it?
We simulated the non-isotopic.
How did you simulate it, and what assumptions did you make in order to do that?
I'd like to reply
No,
to
no,
your
answer,
question.
just answer the question,
Yeah.
please.
So we consider we model all behavior of the air inside the bottle, including heat transfer, compressibility, and airflow.
So you try to prove that the gas inside the bottle would have the same heat at all.
They have a uniform temperature indeed.
Okay, did you investigate the temperature of the coin?
We did not measure the temperature of the
To
coin.
the opponent, do you believe that this should have been investigated?
Seeing as the coin has a much smaller mass than the bottle, I think that it's reasonable to assume. I think that this can be neglected.
Okay, slide number 15 still, please.
Just a sec, please. I'm sorry.
Okay.
What's your question?
Did you investigate the amount of substance that was in the bottle, or did you just assume it to be constant?
We did measure the temperature. In fact,
No, the amount of substance.
the amount of substance.
Yes.
How do you measure that?
No, because it's not my role to.
We did not
answer
measure
that
the
question.
amount of substance because we think
You
that
did
it's
not.
relevant.
Okay.
Relevant.
Thank you very much.
Thank you. Time for preparation for the reviewer. 2 minutes.
Thank you very much, ladies and gentlemen. My name is Mark, and I'm going to present to you the review of problem number 3, dancing coin. First of all, to the reporter, he had a really good experimental setup, which made up for reproducible experiments, and the measurement devices were sophisticated. His theoretical talk approach for critical pressure also was presented in great detail. However, it was unclear where the temperature measurements of the bottle were done. We could clarify that in the clarifying questions, however. I believe that it wasn't really good that you had technical issues during the clarifying questions, because that made it really hard for me to make some statements. And also you had no proof for the assumptions. You answered, and you couldn't really answer the question for the main assumptions that need to be given for an ideal gas law. One assumption for the ideal gas law is a constant amount of substance. And since you didn't investigate the amount of substance, which also is a negative point, we believe that makes the use of an ideal gas law kind of fishy. The experimental investigation of pressure inside the bottle was also something that we couldn't see during the presentation. And you also, in the theory experiment comparison, was not in very great detail. Also because often when you showed those plots, it wasn't clear whether the straight lines were fits or whether it was theoretical approaches. Also with, for example, the simulation for the heat distribution, it looked as if you used the thermal camera. To the opponent, he mentioned very important aspects such as the missing description of one single jump, which we also thought was the main weakness of the report. And he also mentioned the missing variation of the coin radii, which we also thought was really important. He didn't ask for measurement errors regarding the infrared measurement, and he missed on some important points such as the missing description of the gas, which we found really important, and also he partially presented his own theory while discussing about the noise. During the first point of the discussion, they talked about the noise spectrum, and the opponent claimed that the water filling rate is important for the noise production, and the reporter answered that he has done no investigations of the natural frequency of the bottle, and that he has done no experimental variation of that. And we agreed to the opponent that the filling rate is really important, and that this should have been investigated more by the reporter. The next point of the discussion was the slipping of the coin, and what the impact of that was. And the opponent claimed that the deviations of the theory and the measurement is a reason of the slipping coin, and the reporter answered that he couldn't observe such a behavior, and we partially agreed to the opponent that the deviations might have been a reason, even though, for example, the fact that he didn't have a constant amount of substance might also have been a reason for the deviation from theory. The next point was the trajectory of the coin, and again, the opponent claimed or criticized that the relevant part of the phenomenon would have been the investigation of one single jump and the quantification of that, and the reporter claimed that an equilibrium between pressure was what happened there, and he was not able to calculate the angle of the coin over time. We agreed to the opponent, and the motion should have been investigated more. If we look at the task, we can see the main expectations that we could derive from the task. And first of all, the reporter was able to give a definition of what a dance and a noise is, and he could also explain why it happened. We believe that the opposition kind of made that point too big in their discussion, and we didn't think it was too relevant. The next point was how the gas behaved. We think that this was a big missing point in the report. He should have investigated that more, and the opposition should have criticized, and he kind of missed the opportunity to criticize him on that. The quantification of one jump was a main point, and we agreed to the opponent there, and how the dance develops was also a big weakness, since the theory experiment comparison wasn't as sophisticated. Thank you very much.
Thank you very much. Concluding remarks of the reporter, please.
Thank you for the opponent and reviewer. I'd like to start my final report by answering some of the questions that I brought up in our discussion. So, firstly, about the modeling the gas inside as ideal gas. So, actually, we have analyzed the original van der Waals equation, and then we consider the oxygen and nitrogen in the air, which makes up more than 99%. We find that the ideal gas is indeed applicable in this scenario, where both pressure and temperature is not extreme. Following on, according to our simulation, there's only a small region at the bottleneck that has a temperature higher than elsewhere in the bottle. So, and this increase in temperature is due to the boundary condition and also the ejection of the air. And in this process, there will be viscous effects. But generally, most of the part of the bottle will remain at low temperature. And actually, we introduced a dimensionless number called the Boyd number to model the uniform temperature distribution. And by calculating this number, we can indeed obtain the uniform temperature distribution. Moving on, about the measurements of the temperature of the bottle. So we use an infrared thermometer, and we attached multiple metal pieces inside the bottle. And then we can get the temperature of that part by calculating the reflected infrared waves. And we find that the temperature distribution is indeed uniform as the time progresses. Moving on, I'd like to talk about the flipping of the coin, where according to our simulation, the exhausting time of the gas is significantly smaller than that of the dance of the coin. Therefore, the air will returns to atmospheric pressure, and the dynamics will be modeled by a simple rotatory movement under the effect of gravity. And also, the dancing height is uniform according to our measurements. That's all. Thank you.
Thank you very much. Time for questions from the jury. Ilya was the quickest one this time. I was very cautious and looked immediately after I asked.
To the reporter, please. On the slide 15, the data points that you were showing, this was one experimental run or average among several experimental
All
runs?
data points are obtained from 15 experimental runs, and we did draw error bars, but maybe they are small that you can notice.
So that means that all bumps on the curves are systematic, right?
Yes.
Kent?
To the reporter, can I ask, how significant was the thermal mass of the pieces of metal that you put in the bottle compared to, like, how does the temperature of the metal compare to the temperature of the air?
Yeah. So basically, firstly, the metal piece we use is very thin, and secondly, the surface area is just sufficient for IR thermometer to work. So I think that the thermodynamic properties of the metal piece will not affect the overall phenomenon.
Okay, a quick question. So you didn't try in any way to somehow calculate the coefficient for the heat flux or something like that?
The coefficient of the heat flux, I think, is relevant with both the geometry, shape, and surface state of the.
But you didn't try to calculate anything to compare it with your experimental
Yeah,
results?
we did not.
Okay, thank you, Alexandra, and then Eric.
I have this question about the different bottles that you use. In some of the slides, you have plastic and glass bottle, but I think they vary in many different parameters other than plastic, other than material. Did you account for that in some way?
So you may notice that other parameters such as volume is varied. So, but actually, according to our theory, the volume of the bottle will not have effect on the dancing interval and the dancing